Okay, so let me introduce you. so it's bad. Okay, so the next presentation is going to be given by Ahmed. Ahmed is ESR 5G wireless, and he's also a PhD candidate at UPC. He joined us a little bit late, in this project, but he's working on millimeter wave and massive MIMO, both together. Okay?
Okay, I will introduce a low complexity receiver and precoding for outdoor massive millimeter wave MIMO systems. The presentation is organized in introduction and motivation about the problem, then the proposed system of the results and the future work. Okay, let's start with the introduction of millimeter wave for future wireless communications. Multiple communicating devices in and around the body need high data rate to communicate with each other at low latency. And millimeter wave can support high data rates because it makes use of the spectrum between 30 to 300 gigahertz, and the larger bandwidths can support high data rates for device-and-device communications and for Internet of Things. Okay, the challenges. The millimeter wave signals suffer from a severe bus loss. However, they have a small wavelengths, and these small wavelengths permit using massive arrays at the base station and also at the user terminals. And these massive arrays can compensate the bus loss by their own beamforming gain, and they can enhance the spectral efficiency by boosting the multiplexing gain. The transceiver structure per antenna of the fully digital MIMO architecture comprises RF chain and analog to digital converter, and unfortunately these devices are expensive and power consuming, especially at millimeter wave frequencies. Okay, there are many techniques have been proposed to solve the cost and the power consumption problems at millimeter wave. The first is hybrid precoding. Hybrid analog and digital precoding techniques have been proposed with the goal of decreasing the number of RF chains and the ADCs. The spectral efficiency of the hybrid systems approaches the fully digital MIMO architectures. However, the hybrid structures, as we can see, add large number of phase shifters and power splitters and power combiners, and these analog devices can consume significant amount of power, especially with larger arrays. The second technique is using low precision ADCs. MIMO receivers based low precision ADCs consume little amount of power. For example, the power consumption by one bit ADC is very small. However, the using of low precision ADCs hamper the availability of perfect channel knowledge, and it degrades the spectral efficiency of the MIMO system. Okay, the proposed system, we propose a receive spatial modulation technique to reduce the complexity of the receiver of the millimeter wave system. Let us introduce the concept of the receiver spatial modulation. Receiver spatial modulation methods exploit the large arrays at the receiver side to increase the throughput and also to simplify the receiver. In the receiver spatial modulation, part of the input data bits are used to select certain set of the receive antennas to be active. This is the special symbol. However, the conventional receive spatial modulation techniques based on fully digital receiver architectures and can suffer from high performance degradations under correlated channel vectors, which makes the conventional receiver spatial modulation techniques not convenient with the millimeter wave channels. There is only one paper by Marco introduces a low complexity receiver spatial modulation system for indoor line of sight millimeter wave propagation. And this work presents a receiver spatial modulation technique based on novel low complexity receiver and new detection method aimed to increase the throughput under outdoor millimeter wave channel propagation. Okay, this is a block diagram of the MIMO system model. We consider a downlink MIMO that operates in the millimeter wave outdoor narrowband channel model. We consider a fully digital transmitter and a hybrid receiver. We want to simplify the receiver architecture. The black circuit is a downlink circuit, and the red one is the uplink circuit. The proposed receiver based on analog devices like the amplitude detector. For example, this amplitude detector working in the radio frequency domain, and they can detect the amplitude of the received millimeter wave. And this is a phase shifters and 1-bit ADC. We only use one RF chain and 1 fold precision ADC per the downlink and uplink circuits. Okay, let us take an example of the operation of our receiver special modulation technique. Okay, if the input data bits here, the input data bits are divided into some bits for a special symbols and other bits for a modulation symbol. And the bits of the modulation symbol select one symbol from a constellation, for example, a QPCK constellation. We design the precoder at the base station such that if the first special bit is 1, the first antenna will receive a modulation symbol X. If the second special bit was 0, the second antenna will receive 0. If the third special bit is 1, the third antenna will receive a modulation symbol X. After that, this modulation symbol, the amplitude detector, this amplitude detector works efficiently at millimeter wave frequencies with very low power consumption and high sensitivity. And this amplitude detector measures the amplitude of the received signal. After that, the output of the amplitude detector is compared with a predefined threshold. I will talk about this threshold in details. Through using 1-bit ADC to estimate the special bit. So if the received amplitude is greater than the threshold, so that the special bit will be 1. If the received amplitude is less than the threshold, the special bit will be 0. This is a technique of estimating the special symbol. For the modulation symbol, okay, now we estimate the special symbol first, and using this special, the estimated special symbol, we estimate the modulation symbol. For if each antenna is connected to RF switch, and this switch is controlled by the special symbol. For example, if the special symbol is 1, this switch will be closed, and the modulation signal will pass to a combiner. And if the special symbol, if the special bit is 0, the switch will be opened, and it will reject the noise. And after that, all the signals passes through the switch will be combined to the RF chain and analog to digital converter to detect the modulation symbol. So we pass the signal and reject the noise. Okay, now I will go a little bit details in the structure of our proposed system. Due to the severe bus loss of the channel, due to the severe bus loss and the channel vectors correlation of the millimeter wave propagation, the base station selects NA out NR antennas to be active, and the other antennas will be silent during the transmission. Only NA antennas at the receiver side will be active. Okay, based on the properties of millimeter wave propagation, we consider reciprocal propagation environment and TDD communication system. This is a TDD frame. During the uplink training, the user terminal send pilot symbols so that the base station can acquire the channel state information. We didn't consider the errors of the channel state information. After that, the base station selects the best NA receive antennas to be active based on the channel conditions. After that, during the downlink training, the base station sends pilot symbols to allow the user terminal to determine the NA active antennas and estimate the 1-bit ADC threshold. And after that, during the downlink data transmission, the base station transmits the spatial and modulation symbols. Okay, during the uplink training, here the base station, this is the uplink, the proposed uplink circuit. The user terminal sends pilot symbols to make the base station acquire the channel state information. The optimal training pilot matrix for the least square channel estimation can be selected as a discrete free transform basis, and this can be implemented by using the phase shifters, so that we design the uplink circuit based on phase shifters to be low complexity design. And in the downlink training, at the first downlink training, the user terminal want to know which antenna are active. The antenna associated. Okay, the base station in the downlink training sends pilot symbols to the active antennas, such that each active antenna receive signal X, and each or the bad antenna, each bad antenna receive 0 signal. After that, we measure the amplitude of each antenna from all the NR antennas, and we select the antennas associated with maximum NA amplitudes to be active, because those antennas are the good antennas. In the downlink training, is threshold estimations. The amplitudes provided by the good antennas are used for estimating the threshold. We consider the estimation of the problem of the estimation the threshold. Okay, in the precoding and detection. I will now go in details, in mathematical details in the system model. This is the transmitted symbol. The transmitted symbol xij, I represent the spatial modulation I, and j is the modulation symbol j. B is the precoding matrix. B here is the average power. Alpha is a normalization factor. And equation number 2, this is a received signal, where we consider a narrowband millimeter wave channel model based on the geometrical channel model as a contribution of summation of number of clusters, and inside each cluster there are number of rays, and this is the traditional narrowband millimeter wave channel model. Okay, we designed the precoding matrix B as a zero forcing precoder that can be expressed as where HA is the channel matrix from the base station to the selected active receive antennas. We want certain set of antennas to be active during the transmission. And the received signal by the case active antennas can be expressed as this equation number 7, where SIK takes two values, either 0 or 1. SIK is the case entry in the spatial symbol I. If SIK equal to 0, then the antenna will receive only noise. If equal to 1, the antenna will receive the modulation symbol plus the noise. Now, how the base station select the best NA antennas at the receiver side? Okay, for this equation, we want the received signal power to be maximized. We want to select the NA active antenna such that to maximize the received signal power. So the received signal power depending only on this alpha. Alpha is a normalization factor of the precoder. So we want to maximize this alpha, where alpha power -1 equal this expression depends on the channel matrix from the base station to the set of the active antennas. So we want to select the set of the active antennas to maximize this alpha. This problem can be solved by exhaustive search, but the complexity will be high. Low complexity algorithms for maximizing alpha are considered as a future work. Okay, for the thimble detection, the signal provided by the amplitude detector connected to each antenna can be written in equation number 8, square root of the real signal square plus the imaginary signal square, and the PDF of the received amplitude can be rise or Rayleigh distribution based on if the spatial bit is 1 or 0. If the spatial bit is 1, is rise distribution. If 0 is Rayleigh distribution. Now the thimble detection. We consider maximum likelihood detector per active receive antenna to decide if the received spatial bit is 1 or 0. This is the detection problem, maximum likelihood detection problem per active receive antenna. This is a likelihood function given that the transmitting spatial bit is 1 and this is transmitting spatial bit is 0. This is Rayleigh distribution and this is Rayleigh distribution. After some simplification, reach equation number 12. According to this equation, if the received, we want to estimate the spatial bit at each antenna. The spatial bit can be 1 or 0 if the received amplitude is greater than or smaller than certain threshold. We proved the closed form solution for this threshold and different SNR regions. Okay, we can obtain the exact value of the threshold directly by solving this equation, but the complexity of this will be very high because I0 is a zero order modified Bessel function. So this is a high complexity to solve this problem. So we propose a model SNR approximation by replacing the I0 by e power x. This is a model SNR approximation to zero order modified Bessel function. If we replace the I0 of x by this expression in equation number 15, we can reach this equation, and we can put this equation in the form x e power x equal to constant, Where the solution is of this equation, the inverse of this equation is a Lambert W function. So we put this equation in the standard form x e power x equal to constant, and we can get the optimal solution by using the Lambert W function. This is for moderate inner approximation. But also for this, this solution, depending on the Lambert W function, and the calculation of the Lambert W function is not easy. So we make a high SNR approximation. If we can look at equation number 19, at high SNR, the left-hand side can take only two values, either 0 or infinity, depending on the power of the exponential. If the power of exponential is positive, the left-hand side will go to infinity. If negative, the left-hand side will go to 0. So we can take the threshold at the high SNR by equating the power of the exponential to 0, and receive the threshold, and the threshold in this case will be half of the amplitude. Okay, now because of we make first spatial detection, and after that modulation detection. So the threshold should depend on the minimum signal constellation power. The power here in this threshold can be the average power of the constellation. It should be it depends on the minimum constellation symbol power. For example, if we have a QPSK constellation, the average power equal to the minimum power, so the threshold is the half. But if we use 16 QAM, the threshold must depend on the lowest signal power in the constellation. Okay, we proved also expression for the maximum likelihood estimator at high SNR threshold. We consider the estimation problem of the threshold. There is a lot of mathematical details in this part. This is a closed form of the estimator of the estimator. And the error analysis, we evaluate the proposed system performance based on the average bit error probability. The average bit error probability is any number of spatial bits multiplied by the bit error probability, spatial bit error probability, plus number of modulation bits multiplied by modulation bit error probability, where the spatial bit error probability equal half P1 plus P0. P1 probability is that the received amplitude is smaller than gamma, and this one, the transmitting spatial bit is 1. And B0, probability of the received amplitude greater than gamma, and 0 is the transmitted spatial bit is 0. We proved the closed form expressions for these probabilities P1 and P0 in case of using perfect threshold and estimated threshold. Okay, and this is the modulation. This is the modulation bit error probability. The spatial symbol affects the modulation symbol. So we have to consider all the transmitting spatial symbols and all the received spatial symbols in calculating the bit error probability of the modulation symbol. Okay, this is the results. Okay, in the result this represents the average bit error probability of the proposed system and the fully digital MIMO at different constellation designs using 32x8 MIMO systems and 8 transmit bits per data vector. Okay, we compare our system with a fully digital MIMO with single byte decomposition based on precoding and decoding and optimal power allocation for different constellation use. The first curve here is the average bit error probability without the antenna selection. Here we transmit only 8 spatial bits, and we have 8 receive antennas. We don't make antenna selection, and the system performance without the antenna selection is very bad. And this is the best performance are achieved by using 16 phase shift keying. The 16 phase shift keying is a constant amplitude constellation. Because our threshold depends on the minimum signal amplitude, so the constant amplitude constellation makes the highest performance. So using four active antennas at the receiver side and using constant amplitude constellation, the proposed system performance can approach the fully digital MIMO. And this figure represents the average bit error probability of the proposed system under NT equals 32, active antennas equal 4, 16 phase shift keying, perfect and estimated thresholds. For example, the blue curve here is the exact threshold. The circle is the medium SNR approximation. The red is the high SNR approximation. The high SNR approximation approach the exact at high SNR, and the performance reduction is less than 1 dB with respect to the simplicity of the high SNR approximation. And the black lines are the average probability in case of estimating the threshold, simulation and analytical results. The future work, low complexity algorithms for receive antenna selection and considering the antenna selection error, imperfect state information and the base station, the optimal number of spatial and modulation bits to minimize the average bit error probability and the optimal constellation design. Thank you.
Let's look at the numbers.
In 20 minutes. I am running. Okay. Go ahead.
I mean, the obvious remark is that there are too many slides.
But I number everything.
Especially this reason. I mean, if you, this is why you shouldn't put the number over there, because if you say the first time you see 33 slides, and I think there is another one after what there is the reference list or what, but the 33rd slide.
It's not the last one.
It's not, okay. Okay. Then it's even worse because you increase the numbers and then people say, okay, 33 slides, she's never gonna make it. And maybe, of course you can always rush, but that's gives a rushy feeling. So you shouldn't put so many slides. And the general comment about why there are so many slides is that you derived a lot of mathematical steps that you could have avoided because they are kinda standard. Like the fact that you get a threshold decision, to me looked kind of obvious, even though I'm not that into the topic. The fact that you're gonna have a threshold, whatever it means. I mean, in the end you say, okay, I have a threshold, and you prove that. The fact itself that you're gonna have a threshold is kind of obvious. The fact that you derive the threshold in closed form is more interesting, but you don't explain that in the presentation. Also because you actually didn't do that in full detail. In 2 or 3 steps you say, okay, then you derive this and there are some steps I skip. So then why not skip all the previous steps altogether and then just go straight to the conclusion, which would save time. That's my general advice on the presentation.
But I consider all the steps in the proof association.
In certain parts you skip the
Yeah, I consider all the steps.
Yeah, this part, for example, well, the fact that you get the Lambert W function, apart from being, I mean, kind of expected to me, but you can just say that from the very end, from the very beginning. You don't need to derive that. You can put the problem like this and you simplify, then you have the modified Bessel function and this complicate. Then, I mean, why don't you say, we just consider, there are 2 steps actually. I just consider this, which gives me the Lambert W function, and then I still don't want to use that, so I go into high SNR approximation. Thus, I would just say that, which would save a lot of steps. Also because you have to describe the equations, which are pointless. Some of them are pretty standard actually, so this should be skipped anyway. And others are, well, more interesting but difficult to follow, honestly, in this kind of presentation. So I would skip and give the results. If somebody's really interested in seeing how you determine that, they check the paper, at least to me. It is definitely difficult to follow the entire thing. I mean, it takes time. Also, other comments, well, in slide 10. Can you go to slide 10? In slide 10, then, well, yeah, you said this, you discussed this block diagram, and then you said that the interesting part is the AD over there, and you pointed out with the laser pointer. But why isn't it in red? Why there is a red part and not the AD that is the important part? I didn't really get that. I mean, I expected the red part would be something interesting, which actually you didn't mention it. And you go for, you went for the AD part and the ADC conversion, which I understand is important, but why didn't I highlight that instead of pointing at them with the laser?
I introduced, before this slide, yes. I introduces that the power consumption, we have a problem of, we have the transceiver structure granted of the fully digital MIMO comprises RF chain and analog digital converters.
Yes.
And the RF chain and analog digital converters consume a lot amount of power.
Yes.
And our problem want to make the transceiver structure based on the low power consumption devices. So the hybrid architecture reduce the number of RF chains and EDCs and to minimize the power. And for the proposed system, we minimize the RF chains and the ADCs by using analog devices like the amplitude detector, which consuming a small amount of power, which phase shifters consuming very small amount of power, and the power consuming and expensive devices reduce the number of it. Only one RF chain and full precision ADC. This is the point.
Okay, but then, I mean, if you don't point with the laser right here, the entire first part is clear. The fact that the amplitude detector here simplifies the number of RF chains is not evident from this figure. So you should make something better there, like highlight the AD and maybe connect it to the RF chain so that you have just one single RF chain. That's a contribution. Well, it's not obvious unless you point at them with a laser, which is something that if you don't do, it's not clear. So this is not good in the sense that if you print this message that you wanted to convey arrives only halfway, until the point when you say that the RF chain are power hungry, which I agree, and the ADC conversion is power hungry, which I agree, but it's not clear from this point why your solution is better. And also, well, I said most of the things, but yeah. In slide 13, you said something like, okay, I have certain assumptions, like something you wrote down, like reciprocal propagation, TDD communication, and then you said, also we assume, when you recited that, you said, and then we also assume we don't have errors in the channel state estimation, or channel state information. So, well, I wouldn't go for any assumption written down, and just, you said all of them by word, because probably the CSI, the lack of errors in the CSI is the most important assumption. The other are pretty standard, but two are written down, one is a said. So it's a mismatch. Why don't you say, okay, it's a standard scenario, and this kind of assumption, if you feel when explaining them, you feel they're important, you say them. But all this long list of assumptions, blue and black, are kind of stealing attention. More in general, there are a lot of sentences where you put the whole grammar sentence, which you shouldn't. You just should write down like power hungry device, not like high power consumption is due to the presence of RF chains and installed converters. Well, a lot of things like that. This is not very direct as a message. You just say, okay, ADC and RF chains are power hungry. That's it. Same message, but shorter and bigger impact. And also, I had a technical question, which actually not about the presentation, but in the slide, well, in slide 12 or so, you mentioned the QA. No, it's not 12. No, 12. Which one? I think it's 12. No. Yeah, this one. You basically explain everything for a QPSK, and in a sense, this is kind of evident to me, at least. This works better for a PSK modulation because you have the same amplitude. But you never mentioned that. You go as it was for a QAM. And then only at the end you say that, which I understand you want the scenic effect of saying, okay, PSK is better, but it's kind of intuitive here. If you're going to have a threshold on received power, that QAM modulation can be noisy in that you can have a very low power symbol and a very high power symbol, and thus is misleading. Maybe the receiver can be cheated because they say, okay, I don't see any, I just see noise, but there is a low power symbol. So I think you should do some, from the technical side, you should say something more on that. Also because to me, I mean, the modulation works better definitely for PSK. So, and this is true in the end, is shown in the results. So you should say something maybe here. Also because the example just, I mean, explains a QPSK, which is both a QAM and a PSK, so it's kind of misleading, and it makes think that the system works well for any QAM, but actually works better for PSK, if I understood correctly. And in slide 25, I have noticed something. 25. In 25, yeah, okay. You proved, so in the end, you give the full derivation through the Lambert function, and then in the end you reach the threshold is like this. So, and this is again a popcorn muscle kind of equation, because you say, okay, we did a good job, this is the result, it shows that we did our job, we did our good math, and we have this derivation. You don't comment on that, obviously, but wouldn't it be the same if you just keep the whole derivation of the Lambert W function and the Bessel modified function, and you just go straight to this by saying, okay, we did some steps to derive to lower the computational complexity, and we reach this. I mean, that would be the same to me. All the details, I understand you did all the details, but
different types. This is the estimating threshold.
Yes.
This is estimation problem.
yes,
The other, we will prove the threshold. After
Yes.
that, we the receiver side is estimate the threshold. We prove that a closed form for the estimator at the receiver side. So it's different topics.
yeah, probably I mixed them up, but still, this part before that, what was it? Slide 24, what was it? Okay, so, okay, then you're right. But the message is, in this part, you just derived the closed form expression and you said that at the end. In the other part, you just did all the steps. So don't you think this is a bit mismatched? You can just give the result for both parts. That will be shorter, to me at least. That's my message. Okay. So instead of, here you did what was good in a sense. Function is still too complicated, but let it slide. The thing is, you have this expression which you didn't derive. You say, okay, we derived it, and that's it. In the other part of the presentation, you did all the steps, and you reached more or less the same conclusion. You have the expression at the end. So it would be best if you said, okay, we did some steps. Maybe don't give just the results, but say, okay, first we went through the some simplifications, then we went through approximation for high SNR, and then that's the result. But just the result at the end without giving all the mathematical equations, which are kind of pointless. They are good, correct, but they are on the paper. And people will trust you at the conference because they won't bother look at every tiny details that are going to show on the slide for, I don't know, what, 30 seconds. They don't check. Maybe there is even a typo and they don't know. Okay? That's it, I think.
Questions, comments?
Can you go to your results?
Go ahead.
Can you go to the results slide?
Which one?
So you're saying that you're improving the average
Average bit error program.
bit error probability with your system, like it's approaching like the ideal what it should be over here. And you talk about complexity on one of the slides. You talked about the computational complexity. Okay. Have you tried to figure out like what it is actually? Like what is your
The power consumption of the proposed system for high number of receive antennas is 1/7 for the full digital architecture.
Okay, let me say correct. What is the time complexity of actually doing this antenna selection?
Yes. This is a very good question. Okay. In this graph, not antenna selection, but for the estimating the threshold. Okay.
Yeah.
Here the black curve. During the downlink training, the user terminal estimates the threshold. We're using only one pilot symbol to get this curve. By using only one pilot symbol, the performance is very close to the exact threshold. But the antenna selection problem, the error problem in the antenna selection is a future. We didn't go into details of the error in the antenna selection, but we got in details with the error in the estimation of the threshold.
Okay.
And here we use only one pilot symbol.
Okay. So it's pretty fast. Yeah, because if you go into like the real-time systems, then considering how dense the network is, and if you start deploying such systems, this will start to, this will mount up because you have a dense network. So if you're trying to do that sort of selection, then time complexity will come into the picture. And that is why I asked the question. Because you're trying to have a better.
But okay, but the user terminal didn't have to know the channel state information. Okay,
Right.
the antenna selection at the user terminal in this slide, the user terminal will select the antennas associated with the maximum NA amplitudes
Right.
are selected to be active.
Right.
It can be done during one downlink
Yeah.
pilot symbol because the base station directs the pilot symbols in the direction of the active or the best antennas, and for the bad antennas receive zero symbols. It can be done from the precoding and the base station.
Okay.
All the user do is to select the maximum NA amplitudes,
Okay.
and this can be done based on
You know, but okay. Yeah. That's fine.
Could you explain a little bit more why do you choose a line of sight and non-line of
Yeah,
sight
that was
models when you receive the signal and when you don't receive it? The problem is I don't remember exactly the slide, and this would be a problem here.
I mean, if you're
Which
considering line
slide?
of sight.
I can't remember now the slide.
The channel
There is-
model?
Yeah, the channel model, you decide that you use a rise or rally at a certain point.
rise or yes,
The
yes.
derivation.
This. This rise or real distribution.
Yeah.
Or this-
Or the previous one.
The previous one, okay. Yes,
Yeah,
this
here you
one.
decide which. Could you, because I got lost here for some reason.
Okay,
What
this
do you
is
use?
this is the amplitude of the received signal. Okay,
Yeah.
noise is Gaussian.
Yeah.
Okay, here SIK can be 0 or 1.
Yes.
If SIK is 0, then we have noise Gaussian square plus Gaussian square summation of two Gaussians.
Okay.
Okay, it's a real standard of
Ah,
Rayleigh
but
distribution.
That's noise.
It's
It's
not
not
the
noise.
channel.
Okay.
It's not the
It's
channel.
also noise.
It's not the signal, it's just
No,
noise.
it's
that's
just
fine.
noise.
I got it.
But if we have a constant plus noise,
Yes,
it's
sure.
a rise distribution.
Actually, you are considering then only line of sight conditions, I guess.
Yeah, it's only line of sight. But then
No.
what?
Go ahead, sorry.
Do you consider line of sight and non-line of sight
Yes,
conditions?
yes.
Both those situations? Okay. In your channel, I mean.
In the channel, yes, I consider outdoor narrowband millimeter wave channel mode.
Okay, but
But
that's,
this I think this equation not related to the channel mode.
Yeah.
Yeah.
This equation depends on the. If we look here at the. Okay.
is the signal received,
Okay.
right?
Yes.
So it went through
For
the channel,
example,
I guess.
here, this antenna can receive x plus n1.
Okay.
In this case, the received amplitude will be rise distribution.
Okay.
And this antenna, if receive a noise, the received amplitude here will be Rayleigh distribution. So
Yeah.
it's independent of the channel.
Yeah, this is okay, but what I mean is this is signal, this received signal.
Received signal, of course.
So yeah, my question was, well, this went through the channel then. My question
But
was,
we use zero force in decoder as a transmitter side. Zero force in decoder.
which means you are cancelling the effects of the channel.
Yes.
Okay. Okay, I will ask you later maybe if I have more questions for it.
Offline.
Other questions?
Yeah.
It's one
I
matter.
have a commentary that forgot to mention, but I can give it to Ahmed offline. I mean, if we're running out of time.
No, ask. I have a couple of questions
In
as
slide,
well.
in the slide 28, I think there was a strange behavior of the curves. So there are too many curves. But also I didn't get why the 16 QM goes worse than the 64 QM and 4 QM is because of the number of antennas or what?
Yeah.
So the intermediate curve is higher than the two extremes, I think.
The 16.4 QAM. This one.
Yeah. Yeah, it doesn't go like this from the beginning, but
From
for
the
lowest NARs it goes like this. So the
Because
worst one is the 16 QAM, anyways.
Yes. Because I will tell you. Because the case 64 QAM
Hmm?
the minimum symbol power
It's very low.
is very low. That's the
Yeah.
point.
But it doesn't go that bad. I mean, it's either my bad eyesight, but I think But the curves are too easy to be confused. But I think the worst curve is the 16 QAM. Am I right?
16 QM? Yes, this one.
And why is it the worst? The worst curve of 3. I would expect different behavior.
Because the detection not only for the modulation symbol, it depends on the spatial bits and the
Okay.
modulation bits. The spatial symbol affected the modulation symbol.
Okay.
If error occurred in the spatial symbol, for example, if you go to this equation,
No, I understand. You're probably right. But then this means the curve is too crowded because you have too many effects compared.
yes, too many.
You probably should split them.
Mm.
Also, if you want to put curves with the same family, one advice would be not to put them all with the same shade of blue, red, and black, but you can put slightly different colors still in the blue hue, so you can distinguish them better, because it's actually not very easy to distinguish the 16 QM blue line and the 4 QM blue line. They all look alike, because the only difference is the marker there, and the markers are not very, well, the choice of the markers is not very fortunate. They are all similar looking markers. Well, of course they're not identical, but can be, I mean, triangles and crosses and circles would be better, something like that. Anyways, that's very nitpicking. That's it for now.
Okay. Another question. I have just a couple of remarks. So I think that you did a lot of things, really lot of things, and for me you made the usual mistakes that you wanted to tell us everything. So you really wanted to tell us everything that you did. So I think that you should, when you give a presentation, you should understand or identify a little bit what is really the main contribution. Just I mean one thing or a couple of things that you want to tell us, and then I mean just focus on that. Because otherwise, I mean, I didn't really understand, your contribution, what it is, on the developing the threshold, considering the millimeter wave, proposing a low complexity receiver, all of that together, or what? So it's, I mean, it's very hard. Even though you go to the title, go to the first slide.
I
Yeah. Take your time. So look at the title, it's got, low complexity receiver and Precoding for outdoor massive millimeter wave MIMO systems.
I updated this title
So-
with the web. But I couldn't
What
change
is missing? I mean, so
I updated this title, but later, so I can't update it in the presentation.
but look at this. Low complexity receiver and Precoding for outdoor massive millimeter wave MIMO systems. Subtitle: Receive special modulation.
My advisor told me my advisor told me the same comment, and I already changed all the titles, but for the presentation I can. But in the paper I changed all the title. For the presentation, the title is receive partial modulation for massive MIMO system.
Yeah, but okay, that's.
But I couldn't in the
Yeah,
presentation.
just for me to make
Because
focus
it was-
on one thing that
Yes,
you wanna
yes.
because you did a lot.
I received the same comment from my advisor.
Yeah. So when you go to the introduction, you say so many things, millimeter wave, low complexity receiver design, but then I mean I never understood exactly where you focus. Another thing is this is just a more suggestion, but you use if you go through the slide, you have a few figures. And these figures, not the previous one, this one, and the previous one, this and the previous one, this one, these are taken from some other papers, right? So if you take figures from other papers, I don't know if you want other reference, but at least say that this is from somewhere. Because if you find the guy who wrote this paper and you just copy the figure, usually they are not so happy.
From my canon,
That's the whole thing.
which is like not hearing radar.
So another comment, for example, millimeter wave, you didn't get the point
Other noise, which means
because you spend a lot of time on millimeter wave channels.
we can
describing those channels, but then in the end you don't use them at all. You cancel them completely through the 046 precoding.
But there is in the graph, you can see the graph at the end. We consider a millimeter wave channel model, okay, based for the simulations, and without the antenna selection, the performance of the Orbis system is very bad.
Yeah, but you don't, yeah, because you don't exploit your design, right? What you
accounts
the channel.
The part of the antenna selection,
The part of the channel model.
the channel model,
It's where the clusters, where the rays and all this.
how I exploit this channel model in my design. Okay, I agree with you. But the part here of designing, of selecting the antenna at the receiver side to maximize the alpha based on 100% on the channel model. But I agree with you. We didn't exploit the specialist parts of the channel of the millimeter wave channel model to have a low complexity algorithms for maximizing this alpha. But this problem we consider it for future.
Yeah, because I was very surprised, because in the end, I mean, the estimation process that you have for the threshold, etc., is a typical estimation process in noisy channels. So I mean, it does not really come from the channel model, so which was essentially the question that you was asking.
Yes. The only part come from the channel model is the selection.
Yeah.
The selection. But we want to solve this problem based on the channel.
I understand, but just because I mean it's a bit confusing to understand. There is another. If you go to the slide where you have the HSA approximation, ISNR approximation, I found it a little bit strange. First of all, I mean, okay, let's go to the slide first.
ISNR approximation.
First of all, I mean,
This is
no, the figure. There is one for go next slide, next. I don't remember the slides. So the next one. No, the back towards the end. You are going back. Yeah. Go next. This one. So first of all, if you put in the title or if you consider a millimeter wave and then you start telling me that you do an ISNR approximation, I start complaining, okay? Because it's not actually.
of course. But I want to show that this approximation can work at the low SNR, but with very small.
Yeah, a huge gap.
Small gap, yes.
Yeah, but look at
And it's simple
Yes.
at the same time.
But look at that. This is the ISNR approximation,
Yes.
right? The red guy.
Yes.
And then you have the exact one, which is this one.
Yeah.
And then you have
Model
okay. So this is the mid. Okay, so the mean, the mid
Model
SNR
SNR approximation.
is much closer, and the other one, the I is okay. Now I get the point. So no, this was my mistake. I confused the lines. Yeah. Okay. Now I understand a little bit better. Okay. Okay, now I decided to do it better. I think that I confused the lines of these figures because I was actually reversing the things. I was not understanding why it was better in the ISNR rather than the other one. Okay. So this should be okay. Okay, so another suggestion, I think that you should compare it with some state-of-the-art or something like that, because it's just your scheme with different modulation schemes and with different modulation order, different setups parameters.
In the paper, I compared the power consumption
Okay.
with the fully digital MIMO and with the hybrid
The
architecture.
power consumption.
The power consumption.
But not the performance, or you did
The performance only with the fully digital MIMO.
Okay. I think it's good. It's good stuff. Okay. Break.
Please.
Please.